So the virtual memory scheme explains how each process is kept inside its own box. But there are cases where we want a process to be able to reach outside its box. Namely, processes need to be able to invoke system calls, which are basically functions that reside in the operating system. What a process cannot do is simply invoke these functions like they do any other function by issuing essentially a jump instruction. A process doesn't have normal access to the location and memory where the operating system resides. So to invoke a system call, a process has to use a special instruction specifically for invoking system calls. In this instruction, the process specifies which system call number they wish to invoke. The CPU then switches into the privileged mode of operating system code, and then the CPU goes and looks at a table in the operating system which contains the addresses of all the actual code for the system calls. So for example, given this table, if we invoke system call 6, then execution jumps to address FF904444, which is presumably the location in the operating system's memory where that system call resides. When the system call returns, the operating system actually doesn't necessarily resume the process which invoked it, it rather invokes a scheduler, and so it might choose to run some other process immediately thereafter. So in fact, when a process invokes a system call, all the necessary process state is saved so that the process can be resumed later, just like when an interrupt occurs. Again, the system calls exist because processes need the operating system to do certain things for them. When a process executes, it can't do input and output. Those instructions are verboten. If the process tries to use them, it'll cause an exception, because when a process runs, the CPU is running in a lowered state of privilege. So to do privileged things like input and output, the process has to make requests to the operating system by invoking these special functions which we call system calls. And because they are basically functions, very often we need to supply arguments. The usual way that arguments get passed to system calls is the process, say, just might leave some piece of data in a register such that when the system call runs, it knows to look in that particular register to find the argument. Or what a process might do is just leave the arguments on the top of its stack, and then when the system call code runs, it knows to look at the top of that process's stack. So most obviously system calls are used to do input and output, but another thing processes need system calls to do for them is to manage their address spaces. Now, when a program is loaded by the operating system, as we'll see, the code section and the stack section are basically handled automatically. We don't have to explicitly request those spaces in our code. However, when a process wants memory for something other than the stack or for the code, it has to explicitly request it. And this is done with a system call which allocates memory. So if our process wants some heap memory, it requests it from the operating system with a system call in which it specifies how many bytes the process wants. Be clear that this is a request. There are circumstances under which the operating system may refuse. Most obviously, it's possible that the address space of the process doesn't have enough space left to satisfy the request. So the operating system will have to return from the system call a value which indicates an error. When the request is granted, however, the system call will return the address, the virtual address, of where that chunk of memory is located in the process. And of course, before returning, the system call will map the pages of that section in the process. So when the process uses those addresses, they actually correspond to memory in the system, and it doesn't cause a hardware exception. Now, over the course of a running process, that process may end up requesting memory repeatedly. Eventually what this will mean, especially in programs that tend to use a lot of memory or just simply run for a very long time, the process will consume more and more memory, and eventually at some point it's going to exhaust the address space, and there's just not going to be any more room to make new allocations. Consequently, it's important that processes deallocate heap memory when they are no longer using it. This not only helps the operating system better allocate RAM and swap space to other programs, it frees up chunks in that process's address space, and so those freed up sections can be reused in future allocations. It may occur to you that for these allocation and deallocation system calls to work, the operating system has to keep track of which parts of a process's address space are being used and which aren't. When it comes to space for the stack, in contrast, our process doesn't have to allocate or deallocate anything. When a process is first created by the operating system, it automatically is given a section of stack space of some size, and the edge of this space, the so-called stack boundary, is kept track of, very often in a special register. When the pointer to the top of the stack, also usually kept in another special register, when it exceeds the stack boundary, this causes a hardware exception, and the exception handler that runs automatically increases the size of the stack. It maps more memory into the process and adjusts the stack boundary accordingly. So effectively, the allocation of stack space is just handled for us. Unfortunately, this doesn't mean we never have to think about the size of the stack. It's possible that eventually the process either will allocate so much heap memory or use so much stack that the heap and the stack at some point run into each other. That is, when the stack exceeds its current boundary and the exception handler is run, it might be the case that we can't expand the stack any further because there's already some chunk of heap memory in the way. When this happens, there's generally just not much that can be done. So generally it means that the operating system then terminates that process abnormally. This situation is called a stack overflow. The stack has simply exceeded the amount of space that can be allocated to it. So how do we avoid it? Well, depending upon the kind of code that you're writing, it just may not be worth it to you to actually prove that your program will never ever cause a stack overflow. In practice, that's a very hard thing to do, and so it's usually only done for very, very critical code, such as, say, something running in a safety system of some vehicle. In more ordinary code, we simply try to avoid stack overflows by simply avoiding the things that tend to make the stack get really big. Primarily, this means you simply avoid putting large pieces of data on the stack at all. You should put anything that's really sizable, like say more than a few hundred bytes. You should put that sort of thing almost always on the heap, not the stack. The other major cause of the stack size getting out of hand is when you use recursion. If a function recursively calls itself hundreds, if not thousands, or even millions of times, well, each one of those invocations requires a stack frame. So such a function very easily can end up consuming a really big chunk of stack. In practice, most programs which avoid putting big things on the stack or going nuts with recursion, their stacks never really exceed maybe half a megabyte. Getting beyond half a meg or a meg is pretty rare for most programs. There's one last thing we'll say here about processes and system calls. In the life cycle of a process, we can think of it as moving between different states, and most obviously there are four states of first the process is created, and then it moves into the state where it is waiting to be scheduled so it can actually run, and then when selected by the scheduler, it moves into the state where it's actually running, and from there typically a process goes back and forth between the state of waiting and running as it gets scheduled and as it gets interrupted. And at some point the process either finishes or somehow gets aborted abnormally, and so the process is then terminated. The operating system eventually eliminates all of its records of that process's existence. However, when a process is still alive and moving back between the running and waiting state, at some points the process may enter a third state called blocked. When a process is blocked, it's not waiting to be scheduled, because generally it is waiting for some outside circumstance to change so that when it does run again, it can actually get on with its work. The most common way a process gets into the block state is when it invokes certain system calls. For instance, when a process invokes a system call to read from a file, it's usually blocked at that point, because on the timescale of the CPU, storage devices are very, very slow. Like say, if we're reading the file off a hard drive, well, the hard drive may have to spin up and have the cylinders and the heads move into the correct position, and that time can take many, many CPU cycles, which would be better spent processing other things, like say other processes, rather than just sitting around and waiting. So the system call which reads from a file will start the process of reading from the I/O device, but instead of idling while waiting for that I/O device to get its act together, it will put the process into the blocked state and then invoke the scheduler so that some other process or some other operating system code can get some work done. When the I/O device finally has the data ready, it will throw an interrupt, causing the operating system to read that data into a buffer somewhere, and then finally, when all of the requested data has been read into memory, the operating system then puts the process which requested that data back into the waiting state so that then the process can be resumed. So again, processes are put into the block state when they need to wait around for something before they can really continue. This prevents processes from wasting CPU time, which would be better spent executing other processes and other operating system code.